examining the second method now, which is the node voltage. So altogether three methods we've got. Classical methods we've just examined. Now we will be examining the node voltage method. Go inside and we will be examining this method on an example. In this example we've got a circuit. We have changed the circuit that we will be analyzing in this case, not the same as the previous one. In this one we've got dependent source in it to make it a bit different. So in the classical methods we've got 2, 4, 6, 7 elements we've got here. So 14 equations if we use the classical methods. We will be using less number of equations. How many equations we're going to use? We're going to write the Kirchhoff current law equations for the nodes. But pay attention now, since those two elements are connected in serial, I can replace these two elements with one impedance. That impedance is going to be $50 plus minus 100J, that impedance. So therefore, what happened here, I do not need to write another node equation here. So I could do this in frequency domains, but I cannot do it in the time domain. That is the advantages that I use that advantages. So this serial connected elements equivalent impedance is 50 minus 100J. So we are going to write three node equations. These are the three node equations. So let's start from the beginning. In here we've got there are two elements connected to node 1, and both of them the signs are plus because this current reference for this independent voltage source is downwards according to passive sign convention. Both of them coming out of the node, therefore both of the signs plus. The current of this resistor in terms of node voltages is VD1 minus VD2 over 10. That's the resistor current, plus Is equal to 0. Never write Vs here because this is a current Kirchhoff current law equations. If you write Vs here, that means you made a fundamental mistake. Don't do it in exams. Don't do it anytime. Make it a bit better. Now for the second node, the current of this resistor is going to be minus sign, so that minus sign, because for this first node it is coming out of the node. For this second node it is come into the node, therefore this minus sign came in. So the current of this 20 ohm resistor is plus sign coming out of the node, reference current. So the sign is plus. So the current is VD2 over 20. That is the current of 20 ohm resistor. The third current which is connected to that node 2 is the current of that inductor. This inductor current is VD2 minus VD2 over 10J. So VD2 minus VD2 is the voltage of the inductor. If you divide the inductor voltage to its impedance, you get the current. So this is what we have done here. Third one, we've got three elements connected to this one. So current for this inductor, we have already put that in. So the sign is going to change, so minus sign. Now we're going to write here ICCVS, current controlled voltage source current. So once again we are writing current Kirchhoff current law equations. All the terms must be in dimension of current. Never write voltage. This is dependent voltage source. Never write the voltage of this element here. It's going to be this. So that means in the definition relation you cannot see this element current. What you see in the definition relation is this current controlled voltage source voltage is equal 5E. You can write that. This E is this E, another element current. So in this definition relation, you cannot see this element current. So this element current is an unknown, and we've got to write this element current here. So the third element, as we already said that there is equivalent impedance here, VD2 over this impedance gives the current of this impedance. So this is what we have written here. So we've got three equations now. How many unknowns we've got? VD1, VD2, VD3, and IS, IC, CVS. So we've got to write two more equations. So one of them write immediately, supplementary equation. This is VD1. VD1 is the same as that independent voltage source. Independent voltage source in time domain is this. So the phasor of this independent voltage source is just 10 because the angle is 0. So we replace that VD1 with 10 here. We have already done this. So that means we have used this supplementary equation as well. So we've got to write another supplementary equation. We're going to write this equation by using the definition relation of this dependent source. That is the definition relation of this dependent source. If you write this definition relation like this and leave it as it is, this is not the supplementary equation yet. We've got to transfer it to supplementary equation by replacing all the variables here to the variables that I would like to see. This means VD1, VD2, VD3. So 5 times, so current control voltage source voltage is the voltage of this element in terms of node voltages is VD3. The other node voltage is 0, that's why it is only VD3. So we put that VD3 here, 5 is there, so that I is the current of this resistor. In terms of node voltages, this resistor current is VD1 minus VD2 over 10, so we wrote that. So this equation now is supplementary equation. So the number of unknowns and the number of equations are known, so we're going to solve that. Pay attention that the first one, this equation, is not critical because in this equation helps me to find out IS current because IS current is not seen any other equation. So this is left for finding the IS. So once you find the VD1, VD2, then you can calculate that IS. So leave this for a while away. So in here, this is another new variable which is in. This variable is seen only in this equation. That means this equation helps me to find this unknown only. So if you leave this one out as well, what is left? This supplementary equation and this second equation here. So since the VD1, so in this, if you look at those three equations, there are two unknowns, VD2 and VD3. Two unknowns, two equations, you can find that VD2 and then VD3. So this is what is done here. And then once you find VD2 and then VD3 as it is found here, so you can find IS by using the first equation, and you can find the I current controlled voltage source current phasor by using this third equation. So it is found here. So what we have done by using node voltage method, we have find out the node voltages, and apart from that we also find the IS independent voltage source current phasor, also dependent voltage source current phasor as well. So we didn't find all the elements current and voltages yet, but once you find all the node voltages, then you can find all the elements voltages in terms of node voltages. This is what is done here. And then once you find all the elements voltages, then you can find the element currents by using the definition relation. So in here, it has done all the phasors of all the elements current and voltages found, and then all these phasors are transferred to the time domain functions. You see the time domain functions here, they are all sinusoidal functions as we expected. In here we are finding the particular solutions only, therefore one sinusoidal function that we have found. So this method, this calculation might take some time. So whether your calculation is true or wrong, what you're going to do is easy. Do the simulation by using the Proteus, then you can check whether you have done correct or not. Your calculation is correct or not. You can check it by this. Here, what you see here, these are the node voltages, blue, red, and green one, and this yellow one is the IC, this capacitor current. So you see, these are all sinusoidal functions. The only difference is their amplitudes and their phases. Why I am saying their phases are changing? Because they are all shifted sinusoidal functions, aren't they? So that gives you the idea that we found the particular solution, sinusoidal functions only. You could check all these sinusoidal functions, frequencies are the same. How you're going to check it? If you measure the difference between the time difference between those two peak values, you can find the period of this signal. For this yellow one, you can find these two peaks values corresponding time. That's the period of this one. Those for the red one, those two peak values corresponding time difference is the period. For the green one, you can find the period. So the inverse of the period is the frequency, that you're going to see all these signals periods are the same, so their frequencies are also the same. This is what we expected to see. We said sinusoidal function has got three parameters. We're going to find those three parameters, except one of them is an exception. That is the frequency. Frequency of the elements, current and voltages. Sinusoidal functions frequency is the same as the source frequency. You don't need to calculate that. Source is given to you, so you know the frequency of it. So what we calculated here, all these elements, sinusoidal functions, amplitudes and angles that we are finding here. That means you are finding the phasor of it. That phasor determines the amplitude and phase, that is angle of your sinusoidal signal. So time difference, how you can measure the time difference, we could do it here. So for example, this yellow one and this blue one, time difference you can measure. That time measurement is the corresponding time difference between those two peak values. So you're going to measure it here. Time difference between yellow and blue sinusoidal signals. Then one period time is 260 degrees. So this amount of time corresponds to another degree. That degree is the time phase difference between those two signals. So you can check it. So that is we examined this node voltage method. The next method is going to be mesh current method. So we could finish this